Hello everyone, this is Tessa Kegel and this is HBS 5 OHC, Hazardous Substances, Management Systems, Chemical Hazards, Classification and Labelling. So this is Module 3. This is the copyright warning which covers this series of lectures. So first of all, just to go over the objectives for this module. So at the end of this module, you should be able to identify and describe the various physical forms of chemicals in the workplace, analyse and apply information from safety data sheets or SDSs and other chemically related workplace information, access, interpret and apply chemical hazard related information, identify the appropriate requirements for and use of expert assistance, and develop, evaluate and maintain a safe system of work based on accurate information relating to control of chemical hazards. Now, this is a list of readings for this module, and these readings will also be available as a completely separate slide. But just quickly to go over these readings. So readings 1, 2 and 6 are from Pisanello and Tepe, and you can download this from the URL which is listed there. Reading 3 is from the ILO, Safety and the Use of Chemicals at Work. Once again, you can download in the listed URL. Reading 4 is from the Occupational Safety and Health Association from the United States, again able to be downloaded. Reading 5 is actually a set of PowerPoint slides from WorkCover New South Wales, so looking at hazardous chemicals, asbestos and major hazard facilities. And then reading 6 is a journal article by Kegel et al. And that will actually be placed on reserve in the library resources block in LMS. Now, to access that, you can go to the library block, which is on the right side of the LMS window when you first enter LMS. Now, it's important to note that this module will draw on a number of regulatory and statutory references. Not all of these may be relevant to each Australian jurisdiction, but are going to be used to illustrate the principles and applications of the underpinning models and concepts in chemical hazard management. As part of this module, you're expected to source regulatory and other statutory requirements for your own jurisdictions, showing that you have a familiarity with using these principles and concepts. The development, labelling and classification of chemical hazards is complex and ongoing as new products are developed and introduced into workplaces. Accessing, interpreting and applying labels and other hazard information is critical to hazard control. This module examines local and internationally used systems for labelling, including standardised risk and safety phrases, classification systems, including the REACH system, and the globally harmonised system of classification and labelling of chemicals, or the GHS, as well as the use of material safety data sheets and safety data sheets in the workplace. The hazards related to chemicals are generally grouped into 3 main categories. First, physico-chemical hazards of flammability, explosion and implosion. Next, health hazards, which generally affect human beings. And then finally, ecological hazards, which affect the environment. In this module, we'll mainly be concentrating on the physico-chemical hazards. In upcoming modules, we'll deal with chemical hazards which are harmful to human beings. Ecological hazards, though obviously potentially of greater long-term importance than the other two, are beyond the scope of this subject, although you can see from the example of the Whitnum asbestos case that they can be both an outcome and a responsibility of the workplace. Now, it's also important to remember that health hazards and ecological hazards are sometimes very closely related. And this is the GHS pictogram for environmentally hazardous substances. So first of all, when we consider physico-chemical hazards, we look at combustion. Fire is the result of coming together of 3 components: fuel, a combustible material, heat, a source of ignition, and a gas that supports combustion, which is usually oxygen. Materials most readily burn when they are in a finely dispersed state, such as a gas, a vapour, or a dust. Now this is the GHS pictogram for flammable substances. Solids will easily ignite, if they're combustible, when they're reduced to dusts or vapours and are mixed in critical proportions with oxygen. Liquids may give off dangerous quantities of flammable vapours at well below normal room temperature, high vapor pressures, and may form a dangerous mixture with air. Gases are already in their most flammable form. And here we have the GHS pictogram for flammable gases. So the next necessary component of fire is heat, or the source of ignition. Now, the process of filling a petrol tank in a car, boat or lawnmower generates a dangerous mixture of flammable vapour and air. In such circumstances, the exclusion of an ignition source usually prevents combustion. Ignition sources generally found in industry include sparks generated by static electricity and electrical shorts or lightning, open flames such as cigarettes, pilot burners, matches, heaters, stoves, boilers, incinerators and so on, hot surfaces such as heated vessels, pipes, electrical light bulbs, metal particles, embers, overheated mechanical parts due to friction, etc., as well as other ignition sources such as rapid compression of gases, and then there is also spontaneous combustion. And this is the very exciting GHS pictogram for explosive substances. Now, typical industrial explosions may result from chemical, physical, or mechanical processes. And this is the explosion, so a chemical explosion, at the fertilizer plant in West Texas. Now we've already referred to as part of this course, and that took place in April of this year. Chemical explosions result when an unstable compound rapidly decomposes to form gaseous products. These gaseous products, if contained, result in a tremendous increase in pressure, which may burst the container. Some chemicals, such as acetylene, can undergo a double explosion. First, an explosion occurs inside the container, forming hydrogen and carbon particles. Second, the resultant build-up in pressure bursts the container, and the escaping products mix with air and may undergo a further explosion. Now, chemicals fall into a number of categories. We have explosives such as cordite, gunpowder and gelignite, mixtures such as rocket fuels, hydrogen and chlorine, flammable gases such as vapours or mixtures with air, spontaneous explosions of chemicals not recognised as explosions such as acetylene or organic peroxides, and chemicals which react violently with water such as sodium and pool chlorine. Physical explosions result from the sudden formation of large quantities of vapour caused by a liquid coming into contact with a hot material, such as molten metal or hot oil. The largest physical explosion recorded occurred in 1887 when Krakatoa, an island volcano, erupted, pouring seawater into a submarine crater which contained millions of tonnes of molten lava. Now, a common example of a physical explosion occurs when water is poured into a pan of hot frying oil, not to be recommended at home, and as you can see in this image from Kitchen Safety. A boiling liquid expanding vapour explosion, or a bleve, occurs as a result of leaking LPG storage or transport vehicles or even tyres, or when a pressurised vessel such as a boiler, gas tank or tyre bursts. A bleve explosion took place in France in 1966, where a 2,000 litre propane gas tank exploded and 45 people were killed, many of these hundreds of metres from the actual tank itself. Now, the series of photographs below show a bleve reaction taking place. So this was actually part of a field trial, so this was in a controlled circumstance. Now this failure started from a very small pinhole, which soon expanded to a 5 or 10 metre fissure, and a vertical jet was released with the bleve explosion. Dust explosions. Almost all combustible substances can form explosive dust clouds. The size of the dust particles is important in determining whether an explosion will occur or not, and how severe it will be. The most severe explosions occur with particles between 10 and 50 microns. Dust particles greater than 200 microns present little or no explosion risk. As is the case of flammable gases and vapours, there are usually upper and lower concentrations of dust in air which lead to explosions. Typically for dusts, the limits are 20 to 500 grams per litre. Implosions result in closed vessels when a reduction in pressure occurs. Many vessels built to withstand several atmospheres of internal pressure are incapable of withstanding a moderate internal vacuum. Situations which may lead to implosions are heated solutions in a vessel which is closed. As the contents cool, a vacuum results. Cooling of airtight vessels to much lower temperatures, such as cryogenic cooling. Closed airtight containers containing highly oxidizable materials. Pumping liquids from closed vessels. Now, just to finish up this first presentation for Module 3, we've got some definitions relating to physico-chemical properties. A complete list of properties is found in the approved area for classifying hazardous substances from NOSC. The reference for this is in a few slides. Now, in summary, these are flammable or explosive limits and ranges. So substances which form flammable mixtures with air or oxygen do so between a lower flammable limit, below which combustion does not occur, and an upper flammable limit, above which the mixture is too rich to burn. Auto-ignition temperature is the minimum temperature required to initiate or cause self-sustained combustion. Flash point is the minimum temperature of the liquid at which it gives off sufficient vapour to form an ignitable mixture with air. Fire point is the lowest temperature at which a mixture of air and vapour continues to burn in an open container when ignited. Finally, we have spontaneous combustion. When heat, generated by a chemical reaction, is prevented from escaping by some form of insulation, the trapped heat will elevate the temperature of the flammable substance to its auto-ignition temperature and ignite. An example of this is the slow drying of linseed oil, an ingredient of varnishes and oil-based paints. When linseed oil oxidizes in air, or dries, it generates heat. The oxidized components act as an insulator to prevent the escape of heat generated by further oxidation. This leads to spontaneous combustion. Spontaneous combustion needs no external energy source. Now, all of these definitions have the approved criteria for classifying hazardous substances. So this is the NOSC 3rd edition, which is from October 2004. Okay, so we're going to stop now. There are a few readings and some activities for you to do. So first of all, the first reading is Pisanello and Tepe, and we want you to read pages 11 to 17. So this reading introduces the history of industrial chemical use and the hazards related to chemical properties. It presents the conceptual principles underpinning the classification of these hazards and the development of the globally accepted classification and hazard communication systems. Now, as an activity, what we'd like you to do is to identify at least 2 hazardous chemical substances which are used within your work or domestic environment. And using the categories and terminology from this presentation, please briefly describe the potential hazards related to these 2 substances and their related physical properties. And if you could describe the systems you have in place to manage them while being stored or used. And we'd like you to prepare all of this and be ready to share your results in the Collaborate session. The second reading is also from Pisanello and Tepe, from sections 4.2 to 4.3 to the top of page 21. So these chapter sections present the issues and complexities of chemical classifications and the importance of accurate and consistent labelling and terminology.
The second activity we'd like you to do is to select 2 of the pictograms shown in Figure 1, page 20, and then if you could go to the Safe Work Australia website, or at the URL shown there, and download the Code of Practice Preparation of Safety Data Sheets for Hazardous Chemicals, December 2011. And for each of your selected pictograms, if you could use the list tables and lists provided in the Code of Practice to identify the related abbreviation, hazard description, and the related risk phrases or safety phrases, and be prepared to share your findings in the Collaborate session.